Okay, seems to be recording. Good. Okay, so the title of the paper that I'm presenting today is Probabilistic Inference in Language Models via Twisted Sequential Monte Carlo. And this is a paper that won one of best paper awards at ICLR this year. And that's why I've chosen to present it. And the paper itself is very interesting because it has this interesting combination of theoretical and practical things. It's very, very theoretical, but the outcome they're reaching is very useful in practice. And if it is widely adapted, it can make actually a lot of difference in AI alignment and AI safety. So the main problem that the paper is addressing is that generating a response given a prompt can be seen as sampling from a normalized target distribution defined by a certain reward or potential function over the full sequence. But the problem with this is that there are basically infinite number of sequences one can generate given the prompt, because there are a lot of variability. And if you want to actually understand how the distribution looks like and efficiently sample from that, it's impossible because you have to marginalize over infinity, which is very computationally expensive. And this complexity of underlying computational task is the main problem the authors are addressing. So when we talk about, when we talk about sampling from target distribution in context of large language models, there is big space of sequences. And especially given that it is being generated token by token, so word by word, for example. And each decision point in the generated sequence can lead to a million potential continuations. And also the target distribution is very often unnormalized, which means that it is very complex. And it also can depend on the future tokens that haven't been generated yet. And this creates some sort of non-causal structure that when the probability of earlier tokens depends on the generation of later tokens. So the traditional sampling methods that we are using might be inefficient or ineffective in this problem setting. And the challenge is getting even more complex because we want to not only sample the target distribution, not just get the meaning, the sense of the distribution of answers given the prompt, but we want to constrain it by a reward function. So for example, in RLHF, reward function is learned and is defined based on the goal that we want to achieve. So if we want to ensure the model is non-harmful, we will design reward function to prevent all the possible harmful responses a model might give otherwise. And in RLHF, the goal is to maximize this alignment with human feedback over potentially very long and very complex sequences. But as we all know, RLHF has two main problems. Firstly, it's very expensive because you need a lot of human labeled data. And this problem will escalate even further when the intelligence of large language model will outperform to an extent human intelligence. So we will need very narrow domain experts to actually ensure the correctness of responses and things like that. And secondly, it's also quite complex computational to do. And this paper is trying to solve this problem by introducing so-called twist functions. And it's twist because they're modifying, twisting proposal distribution in order to approximate better target distribution. So at every generation step, the twist function is modifying the proposal distribution to ensure the alignment with the target distribution. And target distribution in this way is like the same as target distribution in a real HF. So it's like responsive that will be like non-harmful or something like that. Yeah. But also learning these twist functions and applying is another challenge. And it requires very like deep understanding of like model dynamics and a lot of optimization techniques. So this paper is valuable for like 3 main reasons now, right? So first of all, it makes the suggestion, like proposes this like twist functions. It also explains how to derive them. And it also proposes a method for evaluation of those twist functions. Not twist functions, but a method of evaluation of language models. So it's like bidirectional. Yeah. And now let's look closer at the paper. So the first equation shows us the main logic of the process, how sampling from target unnormalized density looks like. So we see like P0 S1T given as 0 is a pre-trained base model. So S10 is the response, S1T is the response, S0 is the prompt. So if we don't do any manipulations to the model, this is like the distribution that we have. And it has like maximum length of T, which also like mentioned here. And we define the target distribution using the base model, and also it's like modulated by the potential function S1T that evaluates like full sequences. And so the first equation, at the beginning we see the normalization constant. After that we see the base model. And the last term in the equation is this like potential function. And more on that will be later. This also like another point on the normalization constant, because it's also called partition function, but it is often intractable due to the summation over all the sequences, right? As I was mentioning earlier, the parameter, like the space of responses is very large and it's hard to like sample over that. Yeah. And now let's go further. Here, yeah. So when we are talking about evaluating inference in language modeling in general, we can say that sampling from the target distribution is very close related to bounding the log partition function. And the algorithm that was created here shows that it can result in very tight bounds of this log partition function. And they also are saying that tight bounds usually coincide with more accurate target sampling. So the better you can approximate the lower and the upper bound of like this log ZQ, I'm not sure if that's Z, but still, the more accurate sampling will be. And actually the difference between the upper and the lower bounds can also is the same as symmetrized Chi-L divergence between inference sample and the target distribution. So when you want to see the difference between two distributions, the difference between upper and lower bounds can be a good approximator of that. And they are explaining in more detail what are the main contributions of this paper. And as I mentioned earlier, the first one is the algorithm of twisted sequential Monte Carlo for language modeling, which is a way to learn intermediate twist functions for target distributions defined by terminal potential. And the second one is contrastive twist learning, which is a probabilistic method to learn this intermediate twist function because they are like changing, because they are like adapting all the time. And the third one is evaluating inference in language models. So it's like a way to estimate the upper bound of log ZQ. And yeah, it will also help to see the difference between target distribution and inference samples, which is a way to evaluate inference. And we can also see the results much closer here. So if we just look at a typical importance sampling, it focuses on the it works on like sequence as a whole, and it makes it less accurate because you need to wait until like the end of the sequence, right? While the twisted approach, it like re-evaluates and has this like incremental importance weights that are being recalculated at every steps and being like tweaked by the twist function, which makes it like much better in approximating the function that you want to get to. So here you can see like it doesn't matter what is happening before the last like token, and only on the last one we can like evaluate the sequence and categorize it in a certain way. So like green here is like positive sentiment and red is a negative sentiment. And if you look at the twisted approach, you can see that it like reassigns weights at every token, so like sequentially. And you can see how the whole process progresses. So yeah, and this will allow to again like have much tighter bounds and have like much better approximation of the target distribution. Yeah. And yeah.
Quick question. Yeah. When it does this sampling, right? So if I understood you correctly, we take step by step, and whenever we hit something that doesn't look good enough, we essentially cut it short early and might replace that sequence by another one that is already sampled. That is sort of like a greedy approach, right? Isn't there like a risk or that we essentially have to overcome like a little hump in order to get to a value that is like high probability, but because we cut off here, that we essentially only or we reduce ourselves very early, very much.
Yeah, I see your point. It's like similar problem as with like local and global minima, right? Sometimes you need to go a bit in like illogical direction to get like in a better direction in the future. They're not really addressing this point here. They are more like they more like make a point of like moving in the most optimal like direction every time by reevaluating the weights at every timestamp and getting like the highest probability, like focusing on the state at this like current timestamp.
It's probably also depends a little bit on how aggressive you are in those reductions.
Yeah. They are also discussing later filtering. So when they sample like a lot, and after that they like filter out some tokens based on like predefined parameters.
Okay.
So I think maybe that helps it to like make it better. Yeah, and let's talk a bit about simple importance sampling, or how it works.
Also, can you zoom in maybe a little bit? It's
Oh,
easier to see.
yeah. Okay.
The form
Yeah.
will become quite small. Yeah, that's better. Thank you.
So this importance sampling. So what I found interesting is that this like simple importance sampling provides unbiased estimator of ZQ, this variable that we want to have tight lower and upper bounds in order to have good match with the target distribution. And they calculate the importance weights by basically having like the proportion of like ratio of the normalized proposal distribution, which is like Q S1T, and like the current distribution, the like base level distribution. And the estimator is unbiased, meaning that on average, it will equal to a true value of like ZQ. But it doesn't necessarily mean that like every value of it will be like close enough, but on average, it will be the same one. And yeah. So instead of sampling directly from the target distribution, because it will be difficult because of, like mentioned before, problems, we sample from a more tractable proposal distribution. And after that, we just like calculate this like weight and just adjust the proposal distribution accordingly. Yeah, and in order to correct for the fact that we are sampling from a different distribution, from like a proposal instead of the target, we have to compute this like importance weight for each sample. And we can see in equation 4 an example of self-normalized importance sampling, which will take those importance weights and normalize them across all the samples to have the weighted average. So when we have the proposal distribution and target distribution, and this weight represents some sort of error, correct me if I'm wrong, and after that, we normalize it in order to like have the kind of idea. Yeah, Damien?
I can't see equation 4 on the screen.
Up. Better?
Yeah.
Okay, cool. Arvid?
What are the conditions that this sampling function Q has to have, right? So it couldn't be just any Q function, right? Because you need to have some sort of overlap. Otherwise, you might never sample certain points, and because it's an unnormalized distribution you're measuring against, the error could become infinitely large, no?
Yeah, so there are a few ways. So, okay, I'll just scroll a bit further when they're discussing that. Yeah, so here, 3.2 discusses proposal distribution. So as you said, like option A, like the most straightforward, is to just like take the proposal, a pre-trained model to be a proposal distribution. But it will not make much sense because the number of samples have to be like really, really large, because you will have to make a lot of weight updates in order to narrow down parameter space from this like huge like model output, all the possible outputs from the model, to narrow it down to the model outputs that are like harmful in a very, very narrow and particular way. So that's the easiest one, but not recommended unless there is like, I don't know, no other way, because it requires very large number of K. And another option is this like twist-induced proposal, which minimizes the variance of importance weights. And they also develop this like algorithm for deriving this distribution, like based on the twist functions, they're deriving this intermediate target distributions, and based on this target distribution, like proposal distribution will change every timestamp based on the feedback computed on weights.
And the proposal distribution sort of in practice would depend on the pre-trained model, if you will.
Yeah, I think they will start with pre-trained model, but they will update it based on like this twist-induced proposal, like given every timestamp. So they will like take a product of intermediate twisted targets. So like the result of here are they discussing like intermediate twisted targets. So the result of this will be used to like compute the twist-induced proposal. This like here, and we can see like current timestamp divided by the previous timestamp, and normalization plus the proposal multiplied by the twist function.
And because it does contain the p naught, you don't, you at least you're very unlikely to get into sampling issues that that you get blind spots of the model essentially, right?
Yeah.
Cool. Thank you.
But like another question, another issue is actually like deriving those twist functions. And for that, very often we would need to have the reward function. So what they were doing partially is like taking the reward, so like simulating the same RLHF process, and they had the reward function, and they were like trying to approximate the reward function with twist functions. So just like by seeing like how the reward function will behave, they would like update the weights and like improve twist function to minimize this like weight difference and like have very narrow bounds.
So the twist functions essentially iterate as well over the steps.
Yeah. Twist
Cool.
function also like, Okay, and here is the visualization that I was showing previously. And this is the algorithm, how they are doing like basically the sampling. And I think it's like worth taking time to understand. At least I was trying to. So yeah, basically the goal is to sample from target distribution over a certain sequence using twisted proposal distribution. And twist is like achieved by changing standard proposal with the twist functions. So they start for like every timestamp, and for every sample, they sample from the proposal distribution. So each particle is a new part of this sequence that is sampled from the proposal distribution. And after that, a sequence is obtained by concatenating the previously sampled sequence with a new sample. So like sampling the sequence. And after that, depending if this is the last timestamp or it is not the last timestamp, there are like variations of these equations. And the main difference here is the multiplication by either twist function or potential function. So if this is not the last step, if small t is smaller than the large t, we would have the multiplication by the twist function. So this like importance weight for each particle is updated by comparing the probability of new sequence under the base model P0 and the proposal distribution Q that is like twisted by the twist function. And twist function is this like symbol. Yeah.
So when you say particle, right? Particle means we have several candidates that we run in parallel at any point. And is that large K? K, is that the number of particles we...
Yeah, I think K is like the number of tokens. So like
Okay.
if you like sample a sentence, you sample sample from proposal. After that, concatenating like the previous sampled sequence with a new one. And after that,
this indexed by small k, right? So
yeah.
So that looks, we have like a population of k,
Mm-hmm.
right? And we update each of them.
Yeah.
But where do they so we create a population of them, build them to the end, and only then at the very end average
Yeah.
over the total populations to get the Z function.
So it's like nested loop, double loop. Firstly, we loop over like each k, like every like item in the sequence. But for
K is the population, right?
Sorry?
But K is not an sequence indicator. It's like a population indicator, right? Where we have essentially parallel sequence, right?
Yeah. Like sample.
Yeah.
Yeah, every k is like every sample. Yeah. So firstly, we like for each k, so we have like first timestamp, first token, and we have like k samples. We sample like first token for like k sequences. And okay, it's like the first one. And we apply the twist function. And after that, next time we sample like the second token for like each of those k's, each of those sequences. So like t will be 0 and k will be.
Did we lose Tanya, or was it just me?
I think we have. Let me message her.
Oh no.
Okay. Mm, can you hear me now?
You might have to turn off your video. I think it's bad connection.
You're muted.
We can't hear you.
Hear me? Sorry, I'm back. Something happened with Wi-Fi and it just shut down. Okay. I'm sorry. You see the screen? Yeah.
Yes.
So we were in the moment where we are calculating the weights that will be used to update like the direction of the sequence. And the difference in these two equations, like if t small is smaller than big T, it means if this is like the end of the sequence or it's not the end of the sequence. And if it's not the end of the sequence, then we'll be multiplying it by twist function, which makes sense because we still want to like modify the direction, like twist it to approximate the target distribution. But if that's the final step, the main part is the same as the previous step, but we'll multiply it by potential function that is going to be applied like on the whole sequence, and it will evaluate like the entire sequence, unlike the twist function that is focusing more on like intermediate step. So yeah. And after that, for every sample, we will concatenate all the weights in order to get like the total weight for like the sample. And based on that, we will like adjust the twist function. Yeah. And at the end, the thing that we are returning is like ZQ, and the difference between lower and upper bound of this is the same as chi-L divergence between the inferred distribution and the actual target distribution. So like the better we're able to approximate this, the closer we are getting to the target distribution.
One quick question, if I may.
Mhm.
For the second, if t equals t smaller
Yeah.
than t, right? So we sample at any time step. We sample across our population of particles.
Mm-hmm.
It is proportional to the weights they have already acquired up to that point,
Yeah.
or is it only on that point? And then the question is, what is this SK1 to T goes to SWK1 to T? I didn't quite get that.
Okay, can you repeat the first one?
So
The first-
we have the outer loop that goes time step to time step, right?
Mhm.
Then we have the inner loop. In the inner loop, we do the update. We sample for each particle. We take the next token. We calculate this weight WKT, which is the weight of that particle at time t. Yes. And then in the second part of once we have done that, we sample again, but now across the particles, right? So all our parallel sequences, we sample one WKT. And I didn't quite get what we do with that sample, like the after the categorical sampling, what do we do there?
Okay, give me 1 second. I think they were explaining it a bit below. Let me find it. So I think they're explaining it here, if I understand the point correctly. So those resampling steps are done in order to like clone sequences with high incremental importance weights. So as far as I understand it, we want to like capture the high weights, and that's why like they create this like categorical thing, and after that it results in this S1T to the power of WKT, and they use it for like prefix for the next step of proposal sampling. So I think it's a part of like editing the weights and the twist, but I'm not sure.
We sampled K times. This from this we sample from capital K weights K time, or just one time, and copy that one sample all over. It's
I think it's overall K.
yeah. So we sample K numbers from K.
Yeah.
Capital K distribution, but
Yeah. And because it's categorical distribution, it will give us like the highest weights, like
more
sequences with the highest weights. So like the natural selection kind of thing.
But that sort of then means that we potentially we just mix the tokens completely then from the say if we have one distribution is very highly likely, say 99% compared to all the others. It would essentially mean that all the others stop being there, and we just add the new token from that one sequence that was very, very likely.
Yes, but partially it's something we want. So first of all, it's not going to be like, so we want to have high, like few, kind of like more or less few samples with like the highest probability, because we want to like cut from all the sample space the samples that are like the most valuable for like our use case that is defined by the reward function. So like in this case, we will get like case samples that are like the most harmful, like that the model can get, or like whatever we define as the reward function. And like that's why we need to focus on like the sequences with the highest weights and like clone them in order to be able to approximate in the most efficient way and also like time efficient the sequences with like the highest like reward in a way.
It just feels a bit weird that we have our case sequences and each one samples from that distribution, right? So we sample essentially twice, right? We once sample the SK for that line, but whether we add it to any of them depends on all the others, right? And it almost looks the say the first particle, say if K gets large, the chance that you add to your sequence the sample that you have been sampling in the first place becomes smaller, right?
Yeah.
Because
Mhm.
yeah, because SKT, the very first thing we sample, we only potentially ever add if we have compared it against all the others, right? And that almost seems like we're constantly remixing. Say if all the samples were equally likely, then wouldn't we get just random noise out there?
Yeah, but we also have the weights, right? So it's not like we sample just randomly. We sample by trying to approximate like by trying to make the proposal distribution as close as we can to the target distribution.
Yes, but in that step, yeah, in here, agreed. We take that weight, but then we still compare to all the other weights of all the other sequences up to that point, right? And then we, if I understand correctly, in the next step we add a new token to that list, or a string of tokens. But if I understand correctly, that token could come from any of the others, and of course, the more options we have, the more likely it will come from any of the others, because at this point it sort of ignores what its own history was up to that point.
Not sure regarding ignores its own history up to this point, because here as 1KT, like it considers all the previous like responses. So it's like the whole sequence. It's not only the last token. It's like all sequence, and it's being like built up every step. And it's being like updated, as we can see here. So like every step, like we are able to change the direction, like twist it in the direction that will make the upper and lower bound of this Z as small as possible.
Yeah. So in this SK coming from SKW, does it mean we just change the last token, or does it mean we replace the whole sequence essentially with the old particle sequence?
I think it's like let me think. Based on the notation, it would make sense to say that it's the whole sequence, because if that would be like because like from 1 to T, right? So there's like the whole sequence from the first token generated until now, but it's done in order to like change, in order to like manipulate the probability of the next token in a way.
Yeah.
And in
I
order
think
to
it makes more sense. Yeah.
in
Yeah.
order to sum something, it will be like closer aligned with this like WKT, because WKT represents the most like winning sequences that we've seen.
Yeah.
And we want to like have the highest like probability of this like winning sequence, and winning is defined as the difference between like the two distributions.
Yeah.
Yeah.
Yeah. So in any sequence we
Mhm.
but that doesn't mean at any particle we can completely switch it around, because that seems it also gets rid of, say, likely particles again if we find yet another one that is also very likely. So if two particles are the same, there's a chance that they just say flop around, like one becomes the other and the other way around.
What do you mean, like two particles are the same? Like the same in terms of probability?
Yeah. So let's assume we have k particles in parallel, but two of them are very high probability and essentially equally probability. The other one have no probability in after the time update, right? So now let's assume I take the first particle, I essentially roll the dice, and there's like a 50% chance that I either take the one that I already am because I'm high probability, or I just clone the other particle that is already there and overwrite it. Is that correct?
I don't think it's gonna be overwritten because this is like categorical. So it's like there will be like few samples or like few like categories of the highest
Yeah, but
like
this
highest weights.
but this categorical distribution does not depend on small k, right? It just depends on
large K, yeah, true.
the relative weights of all the others, and so yeah. So
Yeah,
even if I am a one of two high probability distributions, I'm essentially 50% chance that I'm gonna get replaced by the other one, no?
yeah, okay, I see. Yeah, it makes sense.
Just found it a bit funny, but if it works, it works.
I
Right?
guess maybe it just like there is a low probability there will be two sequences of like exactly the same probability.
Yeah, or roughly, but I guess it depends also on k, right? But again, if k is very large, the chance that a particle changes its nature to any of the others must get close to one if they are all roughly equally likely after a couple of steps.
Yeah, but like I think there is a difference between roughly equally likely or like equally likely, because still if there is like roughly equally likely, there will be like some difference, and this approach will just like reinforce this difference.
Yeah.
And maybe if they are like roughly equally likely, it's gonna take more timestamps, more t, in order to reach the point of like tight enough bounds to say that it was like a good enough approximation. But yeah, there are like too many opportunities to like get to the point when we have most of the sequences of being like the same probability.
Gotcha. Thank you.
Yeah. And they're also saying here like wire sampling is important, because like if we wouldn't do resampling, it would be just like it would be like a more simple version of importance sampling, where we have this like target distribution and the proposal distribution, and they also showing it here that this is simple importance sampling and this is twisted, and like the main difference is basically resampling every timestamp. And if we wouldn't resample, if we would like simplify this, we would just like go back to simple importance sampling. Okay, we have 13 minutes left, so I think I'll just like show graphs in case we will not have time for that later. So that's the main graph with their evaluation. And remember that I was saying this like log ZQ. The bounds on this is this, like the difference between upper and lower bound is the same as KL divergence between the proposal distribution and the target distribution. And this is how they are evaluating the performance of the model. And this is one of the contributions that they are making in this paper, creating this like new approach of evaluation by equating these bounds to KL divergence. And you can see here, so the dotted lines are approaches when they were using twist-induced proposal. And you can see that if you would use like simple importance sample or Monte Carlo approach, the bounds are like very tight compared to like non-twisted proposal. And I think like non-twisted proposal, yeah, is like the base proposal, like P0, just like taking the distribution. So yeah, this is like the nice visualization. And what else? Okay, now let's go back. Here they're discussing like this twist function, how we approximate this twist function. And in this way, we define the target, the twisted intermediate target distributions, because they would change based on the timestamp. And here we again have like the two cases, like if that's the last time step or not the last time step. And this is the proposal distribution. This is the normalization constant. And this is, if this is not the last time step, it's going to be like multiplied by the value of the twist function. And this is it's like partition function that we multiply by at the end. And here they are like talking again about the way to calculate weights and different proposal distributions that we touched upon a bit previously. So yeah, the simplest way is to use base model as a proposal, but it's going to require a large number of k, as we were like discussing earlier, right? When we have more or less same probabilities for the outcomes, it will take a lot of time to get to the point of our probabilities being high enough. And even if they will be like high enough, we will still not have enough confidence. And this confidence can be shown as big distance, like a huge like bounds, a huge distance between upper and lower bounds. And the twist-induced proposal will minimize the variance. And here they're like discussing connections with reinforcement learning, because partially they position themselves as an alternative to soft reinforcement learning when they are trying to find a way, like another way of approximating this reward function and sampling based on the value of reward function. Yeah. Yeah, so this final potential, if we see it as a reward function, then the twist function can be seen as like policy evaluation of the future reward under the fixed base model policy. So fixed base model policy is, if we consider the base model, which is predicting the next token based like on the previous tokens. And yeah, and here is how we are calculating this. So we are getting the value out of the base model and multiply it by this like final potential when we sampled the whole sequence already. And this will give us like similar results as we would try to apply a policy evaluation of the future reward. Does this make sense? Okay, I will try to clarify. So basically, it's like similar to what we saw in the algorithm, right? That the values that would have higher probability, that would be like more closer aligned with our function, will be propagated forward. And here we can see that like we can make parallels with reinforcement learning in this case. Okay. Yeah. And here they're like discussing the benefits of using this perspective. So why don't we just use reinforcement learning if this approach is basically mimics it in a way? And there are like few advantages. So first of all, this approach allows for more like general target distributions without reference to reinforcement learning objectives. And it has the grounding in like the statistics and the role of twist functions. And this makes it like more naturally motivated from the probabilistic perspective. And also they propose this novel language model evaluation techniques that is like inspired by bidirectional Monte Carlo, which is what I was mentioning earlier, evaluating the like upper and lower bound and treating it as approximator of KL divergence. Yeah, they're also discussing twist learning methods from related work. So before they were trying to use squared error loss, and it was like analogous to soft pure learning. And it will like derive similar squared error loss, but the approach that they are proposing is better in terms of like interpretability of losses, as far as I understood it. And yeah, they did 3 main experiments, and we can see the results here. So the first one is like toxic star generation, and they were trying it to like uncover rare and undesirable behavior. And second one is they were doing like a sentiment task, and the third one is like infilling task. And we can see like the results here. They were applying different methods of twist learning, and contrastive is the one that they developed. And we can see that like here, for example, it scores like the highest, here the highest on like one metric. So it gives like pretty good results. Yeah, and here, that's it. I think that's it for now.
Thank you very much. Very interesting.
Yes, thank you, Tanya.
Amazing. Cheers, Tanya. Catch you next time. Bye.
Bye.
Bye.